Sir, can I start now, sir? Hello. Hello, can we start, sir?
Yes, of course. Should I just start?
Sir, let me start and share my screen first.
Okay.
So good morning and welcome to you all in this third day of FDP on 3D printing and design. We have a guest, Dr. U. Chandrashekhar, sir. He's a program director, advise Wipro 3D Bangalore. He is a researcher, administrator, and keen practitioner of additive manufacturing 3D printing. He has 35 plus years of experience in mechanical analysis, experimental stress analysis, and additive manufacturing. He led ESCI Hyderabad as the director and Weltech University as pro vice chancellor prior to the current job at Wipro 3D. He received his graduation NIT Surathkal and post-graduation degree from IIT Chennai in mechanical engineering. He received a PhD from VTU for his research in additive manufacturing of photopolymers carried out at DRDO. He has advanced diploma in management. His areas of research include mechanical analysis of aerogas turbine, engine modules, additive manufacturing, microaerial vehicles and sensors for harsh environments. He received a gold medal from the former President of India, Dr. APJ Abdul Kalam, for his academic achievements. After serving the Ministry of Defense in several capacities, he rose to the position of Additional Director DRDO in 2010. He set up the country's first ever 3D printing laboratory at GTRE Bangalore in 1997. In his tenure at DRDO, he carried out several technology developments projects and also led a senior group of scientists at Moscow during the testing phase of a development aero gas turbine engine. He received commendation medal from the scientific advisor to the defense minister in recognition of his contributions to rapid prototyping of complex aeronautical systems. He has been invited as a keynote speaker by several international and he serves on the editorial board of international scientific journals. He serves on the academic subcommittee of the National Board of Accreditation for fostering outcome-based education. He is also the current vice chairman of NAFEMS UK's India's chapter. He currently promotes industry institute collaboration in especially metal additive manufacturing through the advice program of Wipro 3D. So with this, I would like to invite Dr. U. Chandrashekhar sir, and it's also my pleasure to introduce you, sir. So it's over to you, sir, to start the session, sir.
Yeah, if you stop sharing the screen, I think my screen will be automatically be visible, no? Or do I need to reshare?
Yes, sir. Yes, sir. Automatically visible.
It's visible. Okay. So let me start the session. Thank you very much for your kind introduction. And I have had the pleasure of getting closely associated with IPS Academy Indore for nearly 5 years now. And there were a couple of occasions wherein I got to address the congregations at IPS Academy on research and development aspects of the additive manufacturing program. And I'm thankful that through this program, I'm able to connect with nearly 200 plus aficionados of this technology under the ACT ATL umbrella. So if you look in the current slide, you see 3 metallic objects on the right side of the screen. Right on the top, you see a very complex shaped flame tube, which is made out of nickel superalloy. In the center, you look at the nozzle guide vane of a gas turbine engine. In the bottom, the the conical structures that you see, which are connected with the small intermediate fingers, it's actually is a feed cluster for a communication satellite called GSAT. And I have not picked up these pictures from any open literature. These were all the projects that we have carried out at Wipro 3D Bangalore during the past 3 years for contributing to the aeronautical, defense, satellite, and industrial pursuits of the Indian companies. So I serve as a program director of Wipro 3D, advise, and one of the important things which we promote through this program is the industry institute collaboration, leading to meaningful research and solutions in the world of advanced manufacturing. My contact details are here, u.chandrasekhar@wipro.com. And please feel free, not only in the current program, but also after the program, in case you are interested in taking up some industry relevant research, or if you want to promote academic pursuits in metal additive manufacturing, feel free to reach out to us and we'll be happy to help you in any which way we can. Now, before getting into the primary subject treatment, let me take your attention to one of the headlines on the second week of August. A company called Skyroot Aerospace, based out of Hyderabad, they demonstrated India's first 3D printed bipropellant liquid rocket engine injector using metal additive manufacturing. So the component that you see in the center of the picture is what we made for this company at Wipro 3D. And fundamentally, it is going to serve the purpose of launching of the small satellites through these launch vehicles called Vikram. Vikram 1 is named after the famous space scientist Vikram Sarabhai. And Skyroot is looking up to possibly it is going to be the first of its kind in India from private sector to develop launch vehicles and help the space missions connected with small satellite. So you can imagine in this specific case, they were able to make this injector using additive manufacturing rather than conventional casting and machining. And in the process, they were able to reduce the overall mass by about 50%. And importantly, they were able to cut down the number of components and the lead time of production significantly. So this is right here in India, and the solution that we developed is shown in the center of the slide. Now let me take your attention to one more news item from June 20, fourth week of June 2020. The world famous BMW company, which is very well known for high quality cars, has set up an additive manufacturing campus in Germany. And fundamentally, what is this campus consisting of? 40 plus additive manufacturing systems dealing with plastics, composites, and metals. And fundamentally, this additive manufacturing campus, which is going to be manned by very few people, is going to develop thousands of spare parts, thousands of new products for the current generation and future generation of BMW cars. So this is a kind of phenomena that has emerged across various sectors, starting from aeronautics to space research to energy to oil and gas to biological industry, medical device industry, consumer goods, white goods. Several places, the additive manufacturing was only connected with prototyping in the initial stage. But if you look at the current pursuits, they are looking at fulfillment of end-use functional applications using additive manufacturing in materials of requirement. Could be metallic materials, could be composites, could be biocompatible materials, could be refractory materials like tantalum, tungsten, which are extremely difficult to handle through normal means or functionally graded materials. Wide array of materials. Incidentally, what is shown on the right side is the venture of the famous company of Elon Musk, SpaceX. So they are looking at making these monolithic engines using additive manufacturing technologies. They are massive in size, extremely complex in geometry, with the small wall thickness, and the entire process is synonymous with time compression while they are developing the reusable launch vehicles of SpaceX. If you look at the additive manufacturing per se as the subject, it has become a point of convergence for various subjects. Of course, the manufacturing is one of the fundamental things, but it's becoming an interplay of design, topology optimization, metallic and plastic materials, laser physics, polymer chemistry, simulation practices, control engineering, post-processing, certification and validation, NDT. So the current practices and IoT enablement. So the current practices of additive manufacturing are no longer confined to a specific department and specific sector. They are becoming all pervading, and it is becoming extremely versatile and multidisciplinary. So I just made a brief mention of what at Wipro 3D we have done. In June 2017, for the project of GSAT 19 of ISRO and SAC Ahmedabad, we worked very closely with the scientist team of ISRO and developed this component which is shown in the inset picture. What is this component? It is called Northwest Feed Cluster. It was a landmark achievement for Wipro. The reason being, conventionally this part was made using sheet metals. It's a conical component, as you see. So they used to do forming of the sheet metals and weld them together. So many weld joints were unavoidable in conventional manufacturing scenario. And more importantly, each of the component has to be located very precisely corresponding to the other component. There are 4 here. You can see 3 and 1 is there in the background. And when GSAT 19 is operating at a distance of 35,000 kilometers from Earth, each of these modules is corresponding to transmission of the data to one zone of India, north, east, southwest, etc. So the positioning accuracy of each of the feed horns is vital for its performance. So using additive manufacturing, we were able to convert 17 parts into single part. It is called monolithization. And in the bargain, the weight was reduced, the time frame for preparation was reduced. And because of the fact that the fasteners like welding joints were completely done away with, the RF performance of the component tremendously improved. So you can see the impact of additive manufacturing on ISRO space mission is so very significant and discernible that ISRO started making many feed clusters for different missions. And in this case, you see a bigger feed cluster of the dimension of almost like 1 meter by 400 mm by 350 mm. And you imagine if it were to be conventionally manufactured, if you have to position one horn with reference to other horn very accurately, if you have to maintain the surface quality inside to superior levels, conventional manufacturing could take several weeks or months. But using additive manufacturing as a standard protocol, currently the scientist team of ISRO and the engineer team of Wipro is able to accomplish these tasks within a fraction of the time that it was taking in the earlier context. So I just want to say that within India at Wipro 3D plant in Bangalore, we have made several additive manufactured components out of nickels, alloys like Inco 718, aluminum alloys like ALSI 10mg, titanium alloys like Ti64, high temperature alloys like HR steels, and tooling materials like SS316. And we applied these components for sensor applications, orthomode transducers, which is a microwave component, impellers in case of oil engineering, oil and natural gas sector, antenna for communication sector, nozzles tips for turbine blades, for small gas turbine, and LP NGVs and high pressure NGVs for gas turbine application. Plethora of applications using the additive manufacturing with various metallic materials right here in India for the labs like DRDL Hyderabad, GTRE Bangalore, NAL Bangalore, Aeronautical Development Agency Bangalore, Vikram Sarabhai Center, VSSC, SAC Ahmedabad, so BHEL, Shell, Boeing. There are several agencies which are connected with the complex systems that made use of additive manufacturing for fulfilling the end use. And we were very happy to be associated with all these things. So fundamentally, I worked in this technology as the faculty member introduced for nearly 22, 23 years. I set up the lab way back in 99. And I had an opportunity or privilege of working with these plastic materials, metallic materials, composites, in components connected with the aviation and to some extent in space technology. So most of the information which I am going to present today is not derived from the literature. It is actually derived from my own first-hand direct applications right here in India. So one of the very famous stories in terms of typifying the progress of additive manufacturing in industrial context is due to the Airbus and General Electric. So the GE developed this component called nozzle tip. And for all their LEAP engines, they were making this nozzle tip using conventional manufacturing. It was consisting of close to 20 parts out of cobalt chrome alloys. Tremendous amount of effort required for manufacturing them. It is a very high temperature component, critical to the performance of the gas turbine engine. Any failure in this component is tantamount to a disaster as far as the performances of the gas turbine is concerned. So what GE did with a concerted effort is converted this conventionally manufactured part into an additive manufactured part. It's called fuel nozzle. You can scan for the complete story at a later time. And as of 2018, GE has made nearly 30,000 of these parts and fitted them for LEAP engine. So each LEAP engine, each gas turbine engine consists of about 20 of these parts. So you can imagine GE has served thousands of gas turbine engines with these fuel nozzles, and they have set up a massive plant with nearly 40 plus metal additive manufacturing systems, and continuously 24/7 they're churning out these components using additive manufacturing. So this is one of the pioneering stories as far as the industrialization of metal AM is concerned in the aeronautical sector. The other sector is the healthcare sector. The currently healthcare sector is catering to the needs of mass customization and mass personalization of the implants through a very good application of additive manufacturing. So there is no necessity for them to maintain a big inventory of these implants, which are not personalized in the off-the-shelf manner. Rather than maintaining a big repository of these implants, they are able to maintain the digital repository of these implants, and depending upon the specific need of an orthopedic intervention, maxillofacial, craniofacial, or for treatment of the patients due to the trauma associated with an accident, they are able to work with the groups involved in the digital manufacturing and develop customized, mass personalized implant. And in many cases, they're able to deliver these implants, which I have shown, acetabular cups, in few days compared to few months that were prevalent before. So the concept of 3D printing hubs is coming to the forefront. The companies like the medical companies like Stryker, they are able to maintain these hubs and enable the availability of these personalized implants, prosthetics, by making synergistic integration of 3D printing into the supply chains. And same is the case with oil and gas sector. Whether you are talking about companies like BPCL, HPCL, Reliance Petroleum, etc., they have got these oil distribution lines or gas distribution lines into thousands of kilometers. There are a lot of components like pumps, compressors, impellers, and some of them can fail. because of the wear and tear associated with the length of service. So how do you ensure the availability of the spare part in the field? Should you be dependent only on the centralized repository for taking care of the spare parts? Then it is not time effective. So what companies which are into the energy and oil gas are into at this point of time is create new models of supply chains. Whenever there is a necessity of a part, then trigger the additive manufacturing route and produce the part just in time and deliver at the point of need. So this is a new supply chain model which has come into the existence in the recent times. The final one which I'm showing is the Ka band orthomode transducer. It is a microwave component. Imagine this kind of, these are always required in few numbers. And the internal surface finish of this component is of the highest level. And the end users in this case are the electronic companies or radar companies like BEL, like LRD. So we have been working with these groups in BEL and DRDO for making these micro waveguides and trying to develop these components without too much of time and cost penalty associated with conventional manufacturing by through portable fusion. I'm very sure this particular slide will be useful to all the students as well as the faculty members who are directly or indirectly associated with Formula cars, Formula student cars, SAE, Baha and Supra competition. I think some of you might have recognized the component which I'm showing here. It is called steering knuckle, or it is also called as an upright. It's a very critical component of the Formula car as far as the dynamics is concerned. What does it do? It holds the wheel hub. It's also connected to the wishbones of the suspension system. The brake caliper is connected to that. Fundamentally, what is this component doing? It is transferring all the loads from the wheel to the suspension system. And it's a part of the unsprung mass of the system, unsprung mass of the car. So if you are able to make this component lighter, there are several functional advantages. Number one, the shock absorption performance of the vehicle gets tremendously improved. And second thing is the drivability or the operability of the car gets facilitated. And more importantly, the students are interested in surging ahead at very high speeds. So you want to cut down the lap time without compromising the safety. The reduction in the unsprung mass of the system can definitely contribute. So look at the system which was conventionally manufactured and look at the topology optimized system which has been realized through conventional additive manufacturing. A weight reduction of almost like 50% and without any compromise in the performance. So whatever are the loads which were acting on the conventionally manufactured parts, they were also simulated on additive manufactured part, and the mass is definitely reduced. The number of parts is also consolidated, and last but not the least, the safety is not compromised and the performance is greatly facilitated. So what we did in Wipro 3D is during 2018 and 19, the student teams from IIT Bombay and a very famous university, VIT Vellore, came and stayed with us for a few days. And using the tools like CAD, Finitelman methods, topology optimization, metallurgical studies, and metal additive manufacturing process of the portable fusion, within 3 days, we were able to outline a framework of converting a component which was performing okay, but which was very, very heavy, into a component which is topology optimized and additive manufactured. And within few weeks, the student teams were able to introduce this component into the working system and into a test bed. And with this kind of the experience, they were not able to participate in the competitions, I think, and one of them got a Creative Design Award for their approach. So what is that I am illustrating is whether you are talking about space systems which are extremely complex in nature, which are orbiting at 35,000 kilometers from Earth, or ubiquitously known SAE, Baha and Supra components, the practitioners, the engineers, the product designers, they can introduce these concepts into their own protocols and realize various multivariate functional benefits by making use of additive manufacturing for end-use application. So let me talk about the research opportunities. 2017 and 18 to 20, we collaborated with IASC and developed India's first electron beam powder bed fusion system. What is this system? How is it different from powder bed fusion system? In this case, we make use of electron beams for melting the particles for fusing them together. And this is also one metal additive manufacturing process. For movement of the electron beam on the surface of the powders, we don't make use of the mirrors. We make use of the magnetic fields. And the speed with which electron beams can move could run into as much as 5 kilometers per second. And more importantly, the power. In case of laser beams, it is typically from 200 watts to about 1000 watts. Whereas here we can talk about 5 kilowatts to 10 kilowatt. So much higher levels of power and much greater speeds of movement. And we don't use of argon environment or inert gas environment. We make use of vacuum here. And using this particular process, we are able to even take care of the additive manufacturing of refractory materials like tungsten, molybdenum, etc., etc. And we are also able to make implants for biocompatible contexts. So this is one tremendous field wherein the engineers from software engineering, instrumentation, physics, mechanical engineering, and metallurgy collaborated together to design, develop, test, and finally convert the entire thinking into a commercializable solution right here in Bangalore. So from this, you can make out what kind of research opportunities are available for those people who are interested in additive manufacture-based pursuits. So at Wipro, we collaborated with several agencies, especially during the phase of March to September, when many faculty teams and student teams were confined to their houses because of the pandemic situations. When there were many calls, we collaborated with each other to develop several research proposals and submit them for very high impact making systems. You can see here what is shown on the right bottom is a mechanical ventilator. It's an emergency breathing assistive system called AirBridge. So many parts connected with the system were made using the May through the time frame of May 2020 to September 2020, and we didn't have access to several supply chain situations, and we had to make use of limited access to design, to the manufacturing, and thanks to the tools. Hello? Yeah. And we were able to make this product and get into commercialization phase. Similarly, we worked with the IIT Madras for making the heat exchangers with extremely complex shapes, as you see here, for lean combustion. And currently, there is an NPTEL program which is on due to the collaboration between IIT Madras and Wipro 3D on the role of additive manufacturing in the future of manufacturing. And we also worked with the BITS Pilani for making the thermal protection systems for human space missions. So fundamentally, in the initial stages, when the metal additive manufacturing system came into existence, the materials were limited in variety. What was happening was we were looking at few cast alloys and trying to manage with these materials for powder bed fusion. But today we are talking about adapting more and more materials, including high temperature resistant steels. Tomorrow, you will see that as the maturity is surging ahead, we'll be designing some of the alloys for the sake of additive manufacturing. And we are looking at aluminum alloys which come at low density with the strength that is comparable to Ti 6.4. So how is it happening? It's happening because of the research looking at process, structure, property. So we are continuously researching on the interaction between the structure, property, process, relations, and fundamentally we are more interested in finding out how does this interaction translate into the performance of the component. So this kind of an approach is a hotbed of a lot of research, and you look at the materials which are available and which are evolving. A lot of materials like Inconel 625, 718, Haynes, Hustelite, stellites, they're all high temperature, creep resistant, high performance, nickel based superalloys, which have been extensively investigated using additive manufacturing. Aluminum alloys like 6061, ALSI 10mg, these are all very famous for their adequate strength at low density. Then look at the stainless steel 17-4, 316L, 15.5, cobalt chromium, tool steels, plethora of options for helping industrial applications using stainless steels. And look at the copper alloys. This particular segment is very important. As you know, the Indian system was in the process of transformation from IC engines to electrical vehicles. Whenever we are talking about electrical vehicles, the developers of the electrical vehicles are interested in making extremely lightweight heat exchangers and battery housings, wherein you will be able to transfer maximum amount of heat at the least possible weight. So continuous emphasis on usage of copper and copper alloys. So if you visit companies like Tata Motors or Bajaj or TVS, Turbo Energy, etc., you can see tremendous amount of focus on induction of copper alloys into the product development. Bimetallic materials, multi-metallic materials. These are also, this is not an all-inclusive list. This is only an indicative list. And last but not the least, just now I mentioned, when you use electron beam melting, you can look at the refractory materials, high conductivity materials, tungsten, tantalum, using additive manufacturing. So by looking at this application, material choices, you can understand what kind of research opportunities are available for the young faculty members. So we worked with IIT Bombay, we worked with VIT Vellore, we worked with ISRO, JNTU, Hyderabad, on various facets of the usage of additive manufacturing for product development, for post-processing, or for material adaptation. So if we have to really categorize the world of additive manufacturing into two lots, typically you are talking about one lot which works with the plastics, the other lot which is connected with metals. If you are talking about plastics, the most important thing is the stereolithography or vat polymerization technique. The system which most of you might have seen is FDM 3D printer, material extrusion 3D printer. Say if you just go into Amazon or Flipkart and you say FDM 3D printer, you can get the printers for as low as 25,000 rupees today. It is just as affordable as your inkjet printer which you are using for printing the document. It has become such a commonplace. All these things will work with plastics like ABS and PLA. I would like to tell you that currently, because of the initiative of Niti Aayog called Atal Tinkering Lab, ATL, more than 6,000 schools in India have introduced FDM-based 3D printing right in the 7th standard. So the students of 7th, 8th, 9th and 10th standards are using CAD 3D printing robotics, using tabletop 3D printers for demonstrating the concepts of physics, mathematics, and science-enabled experiments. So don't be under the impression that 3D printing means fused dispersion modeling and your small tabletop 3D printer which you have got access to. No, the industrial 3D printing is completely different. Industrial 3D printing talks about materials that can meet the end use, like implants for an orthopedic surgery, like the feed clusters for satellites, like the high temperature modules like nozzle guideways and combustors for unmanned air vehicles and turbofan engines, like the impellers and pumps for the oil and gas industry. That is what is industry looking at, not the tabletop small FDM 3D printers where you feed in the data and you print a ABS component. And many faculty members and students have seen that they work for some time on these tabletop 3D printers which cost 50,000 or 25,000 or 1 lakh, and they think that they have learned 3D printing. No, it is a small stepping stone. It's like understanding the multiplications in mathematics, whereas the actual mathematics is much beyond. Like so many advanced concepts you should learn in mathematics before you say that you know engineering mathematics. Okay, so let me try and capture some of these things in my talk. You just take one technology called laser powder bed fusion. This is just one. There are many technologies. In my talk today, for about an hour from now, I limit my presentation to just one or two techniques. The first technique which I'm going to talk about is laser powder bed fusion. It's a possibility that other speakers also might have spoken to you, like Dr. C.P. Paul, Dr. Ravi Kumar, etc., etc. Maybe there is a little bit of repetition. Please, my apologies in case there is a repetition. I'll try to give small industrial perspectives. In case of laser powder bed fusion, what's happening is you've got a laser beam, high power laser beam. In this case, it's a fiber laser, which is scanning on the surface of the component of the powder in a predetermined manner. So a pair of galvanometric scanners are responsible, orthogonally mounted galvanometric scanners are responsible for the movement of the laser beam in the X direction and Y direction. You've got a dispensing platform, which is nothing but supplier of the powder, and you've got a recoater, which is responsible for movement of the powder onto the build platform. Typically, you build the part in form of layers ranging from 50 micron to 100 micron. And as the beam interacts with the powder particles, they melt. And as the beam is moving ahead, the particles, molten particles, solidify. So if you look at the process of powder bed fusion, laser powder bed fusion, there is a phase connected with input data preparation. There is a significant phase involving many software solutions for data processing, and you spend some part of the time on building the part, and finally you have to take the part out from the system and use it. So you have to spend a lot of time, effort, and dedicated approach for post-processing. So what happens in the process is very, very interesting. You please look at the top view of the process. In fact, this particular image is taken at using high frequency imaging, I think about 40,000 frames per second or whatever it is. It's one of the Nature Communications publications. Okay, what is happening is a laser beam is in touch with the powder, and this is the unfused powder. Wherever the laser is in touch with the powder, the particles get melted, and there is a melt pool, a very small melt pool forming below the laser beam. The melt pool dynamics are extremely complex. Actually, the formation of the melt pool, this is the top view, and what I am showing is the front view. The formation of the melt pool is the function of the capillary action, surface tension, and inertial forces. The dynamics of melt pool are the ones which is responsible for producing the part. As the laser beam is moving ahead, the molten particles behind, they get solidified, and you see the continuous ejection of the particles from the melt pool. This is called spatter, and this spatter has to be removed from the process chamber, otherwise they fall and they spoil the surface quality of the part. Why does the spatter happen? It's like, sublimation. Imagine that you have got an ice cube. You heat the ice cube by introducing some heat into the system. What happens? Ice melts. You just imagine that you put too much of energy into the ice cube. Then ice actually not only melts, a part of the ice, without getting into the liquid phase, straight away converts into the vapor phase. This particular process, which you might have studied in your high school physics, is called sublimation. So it's very, very important to understand the melt pool dynamics before we can think of making the part. And look at what is happening to the heat transfer. The heat from the melt pool is constantly driven away from the melt pool because of the conduction to the substrate. But the phenomena which is dominant here is not conduction piece. It's not even convection. A part of it is resulting in the plume, but and there is also recoil pressure. But the important thing here is actually a convection phenomena called Marangoni convection. So for you to understand the implication of all these things, you should clearly be able to find out what happens to the microstructure of the component, what happens to the thermal gradients, what are the consequential influences on the residual stresses because of this laser beam and particle interaction. It is called beam particle interaction. To study this, research groups across the world are spending several efforts, millions of dollars on understanding this process of laser particle interaction. In fact, I think some of you would be knowing the term called synchrotron. What happens in case of synchrotron? Actually, the electron beams are accelerated to tremendously high speeds using magnetic fields. When they are accelerated to tremendously high speeds, they emit light beams with very high energy, and they are channeled down, and they are used to understand what is happening in the material at the surface level and subsurface level. So several studies have been conducted using even synchrotron to understand what is happening to the porosity of the component. So you can see in this case the formation of the keyholes and the effect of the recoil pressure, and all this imaging has been done using a synchrotron at about 40,000 frames per second. So phenomenally, what is an intensive research effort to understand the impact of laser particle interaction on the microstructure of the component. So if you are not able to contain this microstructure, then what happens? Naturally, it will lead to porosity. As I already told you, the conduction phenomena is there, the convection phenomena is there, radiation is also there, but it is the convection which is very, very important in terms of influencing the melt pool dynamics. So this is very famously known as Marangoni convection. In respect of the time constraints, I am not able to discuss all this phenomena. I only wanted to tell you that whether you are interested in the field of imaging, or interested in the field of heat transfer characteristics, or you are interested in the material and microstructure, there is tremendous amount of scope for deploying metal additive manufacturing as the tool and pursue high quality research. And this is one more important process characteristic of powder bed fusion. To some extent it resembles welding, to some extent it resembles casting. It also has got certain features which are common with powder metallurgy. But if you really see, there are many process parameters which need to be controlled. I think the number of process parameters which need to be controlled are more than 25. But if you just look at variation of two important parameters called scan velocity, that is the velocity with which the laser beam moves on the surface, and other parameter which you can easily control is the laser power. And if you draw a PV diagram, laser power versus scan velocity, you get a very interesting, insightful picture. If the energy which is dumped by you into the powder is less, then the particles do not melt. Lot of particles remain unfused. When does that happen? If your laser power is very low and if your scan velocity is high, then you are operating in this zone. It means the power input is less and the beam is moving so fast that it's not able to infuse energy into the system. So what happens? Many particles remain unfused. Look at the other side. You put too much of energy for longer duration, that is high laser power at a low velocity. What is the implication? Too much of energy into the system. So it may lead to the formation of the keyholes. What do you mean by keyholes? Material is vaporized. So you get tremendous amount of porosity. Now imagine a third scenario. You're putting too much energy and you are also moving your laser beam very fast. Then you come into the third implication. This implication is called balling. What does it mean? The material melts, but the molten particles are not able to connect with each other. So they remain spherically disjointed entities. They assume spherical shape because of the surface tension. They melt, they solidify. Neither they are able to connect with the hatch lines which are in adjacent proximity, or you are able to connect the current layer with the previously formed layer. In the bargain, what happens is you get this distinct, disparate balls. So if you look at a specific laser, and if you look at a specific system, and if you are processing a certain material with certain morphological characteristics, it's very important through research and process optimization to understand what is the operating window in which you can assure the making of the part with the necessary structural integrity and strength. Otherwise, either you create a lot of porosity, or you may create a lot of unwanted, you may leave a lot of unfused particles, or you may cause a balling phenomena. So with all these things, you can understand that there is tremendous amount of research opportunity in metal additive manufacturing. Interestingly, the first ever system, which was the foundation for this process, was made in a University of Texas at Austin. And it was called Austin Technology Incubator. Way back 87, an undergraduate student called Carl Deckard, he worked with a professor, Joe Beeman, and he was very fascinated with the idea of converting the CAD data into plastic parts. Those days, he didn't have access to high power lasers. So he was only working with the thermoplastic materials. Fundamentally, during his undergraduate project, he was able to prove that he can convert the digital data into three-dimensional objects. And he got fascinated, and then he continued with his master's and PhD, and ultimately it led to a process called selective laser sintering. And that led to the emergence of a new business vertical called metal additive manufacturing. You might be very surprised to know that the current business volume associated with metal additive manufacturing across the world, connected with materials, connected with processes, and connected with applications, is close to 6 billion US dollars. A billion US dollar is equivalent to almost like 7,000 crores. So 6 billion US dollars is about 40,000 crores worth of business is happening in the world of metal additive manufacturing across the countries. And all this, they had their roots in the initial research work which was carried out in a university way back in 1987. What are the parameters that can influence the quality of the part? It could be the characteristics of the metal powder. For example, when you have got metal powder, when you try spreading on the platform, you imagine that you take atta, try to spread, it has got resistance. You take sand, you try to spread it on a table, it moves freely. You take some clay particles, you try to spread. So each of the or you take iron powder, try to spread. So each of the particles has got, each of the material has got its own flowability, density, morphology, conductivity, absorptivity, the size, the shape, the texture. So all these things are controlled under one category called metal powder. So each of these characteristics has got influence on the part quality, part strength. Now let's look at the machine itself. What about fusion machine? What laser are you using? What is the process chamber containing? Are you making use of nitrogen or inert gas like argon to drive away the spatter? You know, when I showed you the video picture, you saw the flash. What was that flash? There is a violent reaction. The metallic particles are getting ejected. That ejecta is called spatter. You see the similar spatter, similar flashing, even in case of welding also. How do you drive these particles out? And what is the laser power? What is the scan speed? What is the layer thickness? What is the spacing between one hatch line to other layer? All these things, they're controlled in the production. The orientation, what is the support structure? Then you also have got post-processing. How do you do the post-processing? How do you improve the surface quality? What heat treatment you use? And what kind of machining you are using? So if you look at any typical metal additive manufacturing context, there are several parameters which need to be investigated, and all of them offer tremendous R&D opportunities at undergraduate BTech level, MTech level, PhD level, and postdoctorate level. I think in India today, I may not be I may not be exaggerating if I say that there could be easily some 500 plus groups working in IITs, NITs, universities, engineering colleges, on various facets of 3D printing, additive manufacturing, materials, simulation, applications as part of their BTech, MTech, and PhD works. This is one more interesting slide on delineating the implication of chemical and metallurgical aspects, morphological aspects, and mechanical aspects on the quality of the component. You can see this is a component, a turbine blade with a shroud, with a platform, with a fertile root. The surface finish of the blade, when it comes out of the system, is nowhere near what you require. Fundamentally, the aerofoil surface needs to have extremely high quality surface finish to the tune of 0.8 micron RA value to 1 RA value before it can be inducted into the service. So how do you improve the surface quality of the turbine blade, which is made from additive manufacturing? You may have to use processes like abrasive flow machining or MMP or peening to improve the quality. So it gives you tremendous opportunity in terms of process optimization. See, you can increase the heat input. If you increase heat input tremendously, the upskin, that is the surface which is on the top, it becomes wavy. That leads to surface finish. So your RA value becomes suboptimal. If you reduce the heat input also, what happens? The down skin becomes grainy. So that's also giving rise to bad surface finish. If your input quality is not good, then you get staircase effort. So you can see here, just with some simple phenomena called heat input and STL quality, I'm able to illustrate how all of them are contributing to the bad surface quality. So you need to be looking at the surface, whether it is upskin or downskin, whether the data is coming in the upstream activities or downstream activities, to be able to assure the necessary quality in the resultant component. This is an important slide which indicates what are the properties. Many times people ask the question, though they attend the lecture, they will say, sir, can I use the additive manufactured part for end applications? The answer is very simple. When you are using casting, when you are using forging, when you are doing machining, you get certain properties. Tensile properties like strength, yield, hardness, elongation. If the component is subjected to cyclic conditions, it gets the performance gets manifested in the form of fatigue strength or endurance limit. Assess the properties. Some of the data sheets are available. Make similar specimens out of additive manufacturing. Test in your UTM. Test in your own test facilities. All these things, what is shown here, are the tests done at Wipro 3D. You can imagine, you can see in case of aluminum, the strength which you got from additive manufacturing part is far superior to cast part. Similarly, look at the maraging steel. The elongation that we got is much superior to the elongation that we got from the cast part. Titanium, one of the important materials for the aerospace applications. You can see the yield strength and ultimate tensile strength are slightly inferior to what is possible in case of additive manufacturing. It means additive manufacturing is providing better properties than even the cast properties. But where is the sacrifice being done? You can see in some of the cases the elongation characteristics are not as good as the conventional parts. The elongation of SLM parts might be inferior. So one important thing for you to understand is it's essential that you make the test coupons through additive manufacturing. You look at the properties, mechanical properties, compositional properties, and metallurgical properties of these components through your own tests. Look for anisotropy, look for repeatability, look for robustness of your estimation. Only when you are confident that all these properties are comparable to your engineered properties, which are available from casting or forging, then you will suggest to the design groups that you can replace your part with your additive manufactured part. So several groups, as I mentioned, from aeronautical, space, tooling, electronics, energy, oil and gas sector have already replaced conventional parts using additive manufactured part. What is the process of powder bed fusion? To start with, you prepare the data. So you might be using tools like SolidWorks, CATIA tools, or Pro Engineer, or Autodesk, etc., Altair tools. You prepare the data, then you set up your machine, and then you build the part, and then do the heat treatment, post-processing, quality control for converting your CAD data into final part. If you have got proper control on the process, you will be able to compare the macro level, part level, micro level implications. What are the problems that may come? It may lead to deformation, or it may lead to residual stress, or it may lead to porosity. The porosity might not be visible if you are looking at with the naked eye. Maybe you may have to use the microscopy for understanding the porosity. And there is also anisotropy. Compared to what you get in the XY direction, the properties that you get in Z direction could be different. So you need to assess anisotropy, location specificity. The properties that you get in one location, which has got tremendous amount susceptibility to high temperature thermal gradient, might be different from the property that you get elsewhere. So this may manifest in terms of bond length at atomic levels also. So part level, macro level, micro level, atomic level implications are possible in case of metal additive manufacturing. At the part level, you may also look at support structures with a lot of care. Support structures are very important because you need to anchor the component on the build platform using support structure. They're also responsible for removal of the heat from the part to the substrate through conduction. And more importantly, they are also providing the necessary build assistance for overhang features. So what are the support structure possibilities? You can have these perforated structures, you may have block structures, you may have solid structures, and each of them has got an implication. For example, in this case, if you want to build a part of the shape of L, you can have a solid block structure, or you can have a block support with a lot of perforation. It's going to really help you in post-processing. You can remove the support structures of this kind much easily with a manual effort. And if there is unfused powder, for removing the powder through this perforated support structure is much easier compared to what is possible in case of a block supports. So I have taken the example of this steering knuckle or upright, which was done by, as I told you, the students of VIT Vellore and IIT Bombay, just to illustrate the aspect. If you build this particular part in completely horizontal condition, the support structure, which is consequential, can be seen in the blue color, significantly lower. Now, same component is built in the vertical direction. You get higher level, higher incidences of support, including the supports in the circular portion. So you need to spend more time. And the third one is the inclined orientation. The support structures are completely different. Depending upon what number of layers you have got in the Z direction, and what is the type of support structures, what is the complexity of support structures, what is the level of solid fraction of the support structure, many things can get influenced. Number one, the post-processing. The amount of time that you spend on post-processing of the part is directly influenced by the support structures. The other one is the residual stress. Some of the support structures are able to drive away the heat more efficiently than others. The risk associated with the support structure is important. So there are certain support structures which may be solid, but that can ensure the buildability of the part with a greater degree. So would you like to reduce or mitigate the risk by going for that kind of a safety structures? It's again a moot point. Then the number of layers in the Z direction. If you have to build the part, let's say you spend X hours on the system, same part, if it is built in the vertical direction, the amount of time which is to be spent on the machine could be 2x or 2.5x. So your cost associated with the entire process may tremendously increase. And last but not the least, the supports are made from the same material as the original material. You may be surprised to know that the powder bed materials cost anywhere between 5,000 rupees per kg to right up to 30,000 rupees per kg, depending upon the materials and the quality. They are all made through sophisticated technologies like gas atomization or plasma atomization. The particles are highly spherical. They lie in the range of 15 micron to 40 micron in the diameter, 50 micron in the diameter. There is a close control on the size distribution. So the amount of material which is spent on the support has to be minimal. Otherwise, you may end up wasting a lot of material on the support structures, which you would like to minimize these things. So you can do a lot of research, comparative study on picking up the component and understanding what is the implication of one support structure, which is put in the blue color, orientation 1, other support structure, which is in the red color, third orientation, which is in the gray color, and do this kind of a survey or a comparative study. And there is tremendous amount of scope for simulation nowadays. You don't want to get into building of a complex component right away without understanding what are the possible thermal gradients, residual stresses, breakaway situations, delamination possibilities. So you would like to do part orientation, support generation, and simulate all these effects with the help of some simulation software and assess the residual stresses and try to improve all the build parameters in such a way that the problems of residual stresses could be mitigated. When you gain confidence into all these things, then you position the part in a specific manner and then try to gain greater chances in terms of part realizability. How do you do the simulation? By putting in the properties connected with the chemistry, mechanical properties, thermal properties, conductivity, flow curves, etc., as the input to the simulation. And sometimes you may have to feed in the build parameters like laser power, recoater time, the power, efficiency, etc., as your inputs. When you do your simulation with all these inputs, your assessment quality or simulation quality will be so very high that you will come to a condition of declaring the component to be buildable or not very buildable with a fair degree of confidence. So the point which I'm trying to make in this explanation is the additive manufacturing is just not about machine and materials. It's also about usage of simulation techniques in such a way that you are able to predict the buildability of the part. In the recent times, I have seen infusion of artificial intelligence, machine learning protocols, algorithms into metal additive manufacturing in such a way that the entire buildability can be tremendously improved. And when it comes to post-processing, as I already told you, compared to the amount of powder which is there on the platform, we are only using part of the powder, remaining powder continues to be as a powder. How do you remove the powder? And after removing the powder, you need to do the heat treatment and stress relieving, and then do the machining so that a crude looking part like this, which is near net shape, can be converted into a nice engineering component that can fulfill your purpose. So you have to plan either manual processes or processes using integrated powder management systems as a part of your build planning. So this is the snapshot which is taken from Wipro 3D. As you can see, the powder which is unused is being driven away through IPCM conveying module, and sometimes it becomes a necessity to either vibrate the build plate or rotate the build plate and use compressed air and inert gas for cleaning and removing the powder. Otherwise, the powder gets trapped and you will not be able to use it once it is permanently stuck to the platform during the post-processing. I've gone back to the component of bi-fuel liquid engine rocket injector, and you can see in this case, we understood that there could be a lot of powder entrapment, and we intentionally introduced these small triangular cutouts into the part because of the fact that we wanted to remove the powder without any hassle in the post-processing. If you see, this triangular cutout is not part of the original design. It has been introduced for making the part friendlier to additive manufacturing. And similarly, introduction of these perforations into the build support structures. What is the purpose of this? On one side, they provide the support. On the other side, they provide necessary perforation through which you can remove the unused powder. And you want to remove the part from the build platform. What do you use? You may use a bandsaw, you may use wire EDM, or you may even use a hacksaw. What is the amount of allowance which you need to provide so that you can remove the part confidently? It depends on what is the material you are working on, what is the extent of coverage of the build platform, what are the absolute dimensions of the build platform. For example, if you are working with the titanium on a system called M400, which has got a build dimension of 400 mm by 400 mm by about 500 mm in XYZ direction, the allowance that you need to provide for the part is much higher compared to dealing with aluminum on M290 machine. So it is very important to understand that each of the build parameter has to be properly looked into depending upon certain characteristics of the build material, build process, and the system that you are using. You make a part and you look at the strength of the part and you think that there is a provision for improvement. Then depending upon the factor, whether you are looking at ferrous alloys or non-ferrous alloys, you may do annealing, tempering, hardening, case hardenizing, and the impact of all these things will be tremendous in terms of improving the tensile strength, yield characteristics, the elongation at modulus, at break, and last but not least, the hardness. In this case, you can see Inco 718, a nickel alloy which has been heat treated, had a quantum jump by almost like 50% in the hardness from 30 HRC to 47 HRC because of the heat treatment on the additive manufactured part. And similarly, surface treatment. The surface may not be optimal in terms of its quality. Even the dimension quality may not be good. So you may use tumbling with a tumbler or short peening, electrochemical polishing, abrasive flow machining, where you put some abrasive particles into a medium, viscoelastic medium, and then the paste-like material carries the abrasive particles and it goes into the cavity, removing the surface imperfections. And you may also use electroplating to improve the quality of the surface. So all these things come under post-processing. I'm showing one turbine blade which we made. It had aerofoil and it had a dovetail and it had a thin platform. So what did we do? We don't want to touch the aerofoil portion after building, but we had to polish this dovetail because That is the position where it is fitted into the disc. So we did all the planning right in the beginning. You can see here, while holding the airfoil portion, which is a delicate portion with the proper fixturing, we were able to do the necessary machining on the dovetail root and able to provide necessary surface finish that meets the assembly criteria. And it's not a must that we have to do each and everything in powder bed fusion in additive manufacturing system. For example, look at this component called pedicle screw, developed out of Tie 64 at our plant nearly 1 year ago for implants for animals, for veterinary applications. So the screw portion of this was not made in additive manufacturing. What we made it was like this. After that, we spent enough time using conventional manufacturing processes to get the fastening features. So the post-processing can be used as a powerful enabler for improving the functionality of the part to whatever you desire to do. So if you come to Wipro 3D, we talk about build technology called powder bed fusion. We also have electron beam melting. We have got even plastic additive manufacturing. That's only one part of the story called build technology. But with that, you're only getting 15 to 20% of the necessary talent. What is very important is you need to develop your design approach. What is the value addition you can bring into the part by reimagining the design? Do you want to cut down the number of parts? It is called part consolidation. Do you want to reduce the part weight? It's called lightweighting. Do you want to improve the functionality of the part? It is called functional integration. All these things will make manufacturing process much more powerful than conventional manufacturing, because you are able to advise the design groups to relook at some of the features and reimagine the designs. So all these things require engineering design approach and additive design approach. It involves application of simulation tools also. Then I talked a lot about post-processing. Post-processing is a mixture of so many processes connected with surface, connected with dimensions, connected with microstructure. So you need to know little bit of all these processes to be able to translate the usage of this additive manufactured part to a serious application. Then are you looking at small set of materials, or are you looking at adapting new materials? It's a complex situation. I will show when we were recently working with HAL for a helicopter engine. They said, please make this turbine part which is made out of a special purpose steel. So we had to do a lot of research in developing the process parameters corresponding to the fitment of this material for powder bed fusion process. Then comes testing and validation. I make a part. For example, you are interested in your Baja and Supra car. I make a steering knuckle upright and I give it to you. You may not really believe that that is safe enough for usage. So you may do a lot of measurement. You may do testing in your college with your car before taking it to the competition. So if you are looking at implant, the surgeon would like to do a lot of testing. So testing, validation, certification is a very important phase of research as well as development. So NASA has worked with a lot of technologies in metal additive manufacturing, and they have published many interesting literature, many case studies. If you look at the build envelope of the component which is available in Wipro, one of the machine has got 250 by 250 by 250 mm build envelope. Other machine has got double that. But look at the parts that you can make for rocket engine. Some of the parts have got a diameter in excess of 2.5 meter. These Southwest Research Institute, along with NASA, has published several reports on how they are making the large-sized parts for rocket engines using additive manufacturing. There seems to be no problem in terms of producing large-sized parts. We made this part in Wipro 3D in 2018. It has got a diameter of 1 meter. And you can understand this particular part for anti-icing article of a gas turbine engine. What do you mean by anti-icing article? Imagine that your combat aircraft like Tejas is flying in a place like Leh Ladakh. So the ambient temperature could be very low. So ice may get formed in the frontal portions of the gas turbines in the aircraft. Once there is a serious dip in the input air temperature, the performance of the gas turbine can tremendously come down in terms of lower thrust level. So what do? You need to melt these things. How do you melt? By introducing some hot air into the frontal portion. That is called anti-icing. So this entire anti-icing article was produced by Wipro 3D with a combination of conventional manufacturing, additive manufacturing, and the size of this particular thing is more than 1 meter, and it's made out of titanium alloys and nickel alloys like what you're seeing. This is an engine for unmanned air vehicle which we made. It is called flame tube. You can see in this case there are 12 swirlers, and the swirlers are actually churning the mixture of air and gas, air and fuel, and vaporizing them. And these air fuel mixtures are burnt at temperatures like 2000 Kelvin in the combustion chamber. So if you were to employ conventional route, it could have taken 5 to 6 months. We made it in less than a month's time, and the part is undergoing testing. This is called flame tube. Similarly, this is the part which we have made for the HAL helicopter. The part is called inner ring. It is made out of a special purpose steel. And in this case, why were we doing? I think you might have heard the government has given a message called Atmanirbhar. For several decades, our armed forces, Army, Navy, and Air Force were dependent on the sources from Russia, Italy, France, Israel, etc., for the spare parts. And whenever you are dependent on the foreign sources, a lot of time is spent on procuring the spare parts, and the spare part cost could be so very high because the OEMs want to make a big profit out of it. So now our armed forces are trying to develop self-dependence by looking at indigenization of all the spare parts using Indian manufacturing ecosystem. This is one more component which we made for waveguides, and fundamentally the component is called orthomode transducer, and it's also known as polarization duplexer. It combines two orthogonally polarized microwave signal paths. What is very important in this case is the internal cavity, which is very circuitous in this case, has to have tremendously high quality of surface finish. Then only the necessary microwave performance can be ensured. So we had to develop a post-processing methodology for this particular process. So if you look at what is the situation that is prevalent in India, it's not a complete listing. Automotive companies, research companies, aerospace companies, tool rooms, many jewelry manufacturing companies, medical centers, engineering service providers, startups, academia, incubation centers, etc., energy and gas sectors, they are using metal additive manufacturing in their centers as a part of the product development, as a part of the re-engineering, as also part of the repair and refurbishment of the used parts. That particular phenomena is called aftermarket. After the product completes its life, how do you extend the life of the component? This is called aftermarket. Oil and gas people are making use of the parts and testing them for corrosive property, anti-corrosion, and strength using various test rigs. Several agencies have developed the standards for accepting the part. See, I think some of you might be familiar with ISO standards, ASTM standards, SAE standards. There are standards which are available in the world today from several agencies like ASTM, AMS, ISO. How do you make the parts? How do you test the parts? How do you accept the parts for various applications? Standards are available. So if you follow the standards, you will not have problems connected with the microstructure, connected with the strength, connected with the application, and of course the property. So what I would like to do is, it's almost like 11:55 now. There are many more things which I would like to show. Last year when I went to a famous additive manufacturing exposition called Form Next, I came across this technology, and you can see here a very large marine gas turbine housing made through additive manufacturing technology called DED, direct energy deposition. What is happening in this case is you got a laser beam, and as and into the path of the laser beam, you are continuously injecting the fine particles, and the laser beam remains stationary. The build platform on which the part is getting built, it is rotating, it's also articulating in the XYZ directions. So you are able to get an extremely complex part with a stationary laser beam, and you can see, and you can induct this kind of parts into serious applications of this kind. So you are getting more and more applications of this kind. Currently, a lot of calls are open from Department of Science and Technology, Department of Biotechnology, AICT, etc., etc. Hello, for research connected with additive manufacturing. If some of you are interested in this research, feel free to approach me. I would like to conclude my talk at this point of time because I want to spend about 5 to 6 minutes on the taking of the questions and answering them. My email is here, and if some of you are very keen to develop greater skills, application abilities in industrial practices of additive manufacturing, you can approach me. If some of you want to develop focused programs, a lot of IITs and NITs have already started additive manufacturing courses, 3-credit course, 4-credit course. Why? Because in the engineering sector, core engineering sector nowadays, jobs are limited. Most of the engineering students are going only to the software sector, but jobs are being rediscovered in the core engineering sector if you can develop your design skills, topology optimization skills, mass customization skills. You can get a lot of jobs in the IoT sector, industry 4.0 related applications, medical sector, automotive, e-vehicle sector. So many NITs and IITs have introduced these subjects. Very interesting. It contributes to the startup ecosystem also. Just 3 days before in the Startup India competition, I saw that 3 Indian 3D printing startups have got the highest level of recognition in the awards. So many things are happening in the world of additive manufacturing in India. So if you are interested in the research aspects, I recently collaborated with Bharat Vidyapeeth University, Pune, BITS Pilani Goa campus, IIT Madras, IIT Bombay, Indian Institute of Science, Bangalore, Centurion University, Bhubaneswar, for several aspects connected with additive manufacturing of metallic materials and plastics, connected with the defense applications and aerospace applications. And it requires some commitment on the part of the faculty, commitment on the part of the institution. Last but not the least, some effort beyond to introduce them into curriculum and introduce them to the research. So thank you once again for this opportunity. I'll be happy to take some questions and give answers for about 5 to 10 minutes. And I request the organizer to unmute those of the people who want to ask the questions. And I would like to close my presentation now. Thank you so much.
Yeah, thank you so much, sir. I welcome all the participants. Please ask the question.
Sir, very good morning, sir.
Good morning.
Sir, before I ask the question, I would like to say one thing about your presentation.
Yes, sir.
I was thinking that I know something about additive manufacturing, but after listening to you, I came to know I don't know ABCs of this additive manufacturing, sir.
No problem, sir. Even Einstein used to say the same thing, Maybe he discovered the theory of relativity, but he doesn't know basic things. So it's a big world. It's a big world. Where are you from? Kindly say all the participants, kindly introduce yourself with the name and the institution you belong to so that others will also come to know.
Sir, I am Venkatramana from Andhra Pradesh, Vemu Institute of Technology, sir.
Vemu Institute of Technology. Okay, right, sir. Please ask me the question, Mr. Venkatramana.
Sir, my first, you are saying in the perspective of research, but I want to ask in the perspective of entrepreneurship, sir. Can I ask?
Yes, please.
Sir, what are the knowledge areas that is required for an entrepreneur in the additive manufacturing?
Yeah. An entrepreneur requires certain skills, certain characteristics, whether it is additive manufacturing or whether it is other area like artificial intelligence, machine learning. He has to have necessary technical competency. And second thing is he has to have an ability for providing additional value, a different kind of a value proposition, then only there is a business case. So to answer your question in a very brief manner, there is a technical content, there is a business content. Both of them together only contribute to entrepreneurship. I'm just happy to say that currently I'm mentoring 3 startups in various places, including Andhra Pradesh, Orissa, and Karnataka, connected with additive manufacturing. And I have always seen these entrepreneurs are successful because they are combining the technology along with their business acumen.
Sir, what are the problems we'll be facing while manufacturing with additive?
The problems that are connected with additive manufacturing are the problems connected with any other process. When you do casting, you get porosity, you get hot spots, you get tears. When you do machining, you get cracks. Sometimes the parts will be out of dimensions. There are tolerance issues. So please understand that additive manufacturing has not come from outside of the world. It's also one of the manufacturing processes. Like any other manufacturing process, like forging or casting or sheet metal, EDM wire cutting, process parameters need to be controlled. And if you don't control, some defects can come. So there are no specific things connected with only additive manufacturing. Even if you take casting, casting as a technology is known to mankind for 400 years. But even today, if you go to a casting shop or a welding shop, you will get cracks, you will get defects. So every field there are possible problems.
Yes. Sir, is there any textbook or a literature where we can understand the mechanism of adhering one layer to the another layer, as you are saying the laser thing?
Yeah, there are lots of textbooks. Unfortunately, Dr. Venkatramana, the textbooks provide uh, highly mathematical treatise of the subject. So many times people get scared because they show laser particle interaction using many equations and mathematical aspects. The best method of understanding this is by doing on your own. Yeah.
Sir, if a person want to start become an entrepreneur, let me say his capital investment is around 20 lakhs. What is the best machine that he can choose, and what is the best area in which
Dr.
he can start?
Venkatramana, is my first slide available? The reason is I will get into deeper discussion with you because nearly 200 participants are there. So send a mail to me.
Okay,
My
sir.
phone number is 63740 You can talk to me later because now I want to take the questions from others.
Thank you very much, sir. Thank you very much.
Sir, some participants are also asking in chat box. Sugannath Valumani is asking, sir, which software used for thermal mechanical analysis in your slides number 2?
Yeah, we are using many software, including the software provided by materialized people for build planning. And when it comes to simulation, there are in-house software as well as Altair software, which we are using for prediction of the residual stresses. Yeah.
Hello, good afternoon, sir.
Good afternoon.
This is Ashwini Joshi from IPS Academy Indore.
Yes, please.
Sir, is there any limitation of manufacturing any particular shape components in DED, like any sharp-edged
See, I have shown
component?
you all kinds of components, starting from steering knuckle to space parts to gas turbine parts, I think having seen all the parts in my presentation, you should have by this time gotten a feeling of the complexity with which we can make the parts. Actually, I would like to say, Dr. Ashwini Joshi, higher the complexity of the design, better are the chances of using additive manufacturing.
Is
Understood,
it
no?
possible for sharp-edged components also? It is possible that because
Yeah.
when we are
Yeah.
creating sharp corners, it
What do
is
you mean
more
by sharp
chances of.
corner? Dr. Joshi, I will just tell you that people have used biological tissue to make components with a submicron accuracy, micron level accuracy. Okay.
Yes,
Two, they have made use of nozzle guide vanes which have got a sharp corner of 0.3 mm to 0.4 mm using these materials. So my answer to you is a big yes.
yes. Okay. Thank you, sir.
Yeah.
This is the last call of asking the questions. Please ask if you have any questions. After that, we will conclude the session.
How to predict the SLM parts using data set or images is a question asked by one of the participants. I could not see the name. It just popped up. And what is the
Sugnath
name?
Valumani. Sugnath Valumani is asking.
Yeah. Which is it specific to a material or process? Can you just unmute and ask the question because the question is not
Yeah,
clear to me.
that will be better.
Good afternoon, sir. I'm asking to related to metal printing.
Okay.
How to predict the there is a printing of metals. A final
Which
finishing,
metal?
we will detect the quality of the
Which metal?
printed products.
Which metal, please?
Like titanium, AL6 20 grade 23.
So if you know the conductivity of the material, absorptivity of the material, specific heat of the material, scan
Okay, sir.
speed, and the laser power, there are analytical models by which you can assess the energy density. And once you know the energy density, you will be able to even assess the implications of the residual stresses. This is a
Okay, sir.
short answer.
I need to see your slide in step 2 and step 1. I need to see that
What
parameters you have chosen that for predicting
There
the.
there are machine parameters, there are material parameters, there are process parameters, post-processing parameters, input data parameters. So there are close to 30 parameters which need to be controlled. It's not a small thing. I told you that the parameters are also connected with the materials, particle size distribution, morphology, flowability, density, and chemistry. So the parameters are just not limited to the process alone. They're also connected with materials.
Okay, sir. Thanks. Thanks,
Thank
sir.
you. Thank you. Okay. Dr. Mayank, I
Yes.
think we are through with the session now.
Yeah.
And yeah, Mr. Venkatramana, if he is there in the session,
Yes, sir.
quickly call me in the next 5 minutes.
Yes, sir.
And thank you, Mayank, for this opportunity. Can I close
Thank
the
you.
session now, please?
Sir, I would like to give thanks on behalf of Department of Mechanical Engineering, IPS Academy Indore. I think you have covered all the contents like industrialization of 3D printing of metals, aim of structural components, topology optimization, and evaluation of metal and materials, business aspects of these 3D metal printing, and various factors influencing of metal printing and also the post processing. So thank you so much, sir, for your nice and wonderful presentation. I hope the participant will get the idea and will take a pledge to give something this knowledge to the students and will help in their project.
Thank you.
Thank you. So there is a break of 30 minutes. We will meet in the next session by 12:30. Thank you so much.